Now, in particular, just as the slope of the tangent line has this notation, or this notation, at the point x equals a, perhaps. You know, you're at some point and you want to look at the slope of the tangent line there. There's a similar notation for the area. The area under the curve. So I'm going to give you two different curves here. I'm going to build it up in two different ways. Let's say that this is the function y equals f of x. And let's say we want to find from the point A to the point B on the x-axis. Let's say we want to find this area. Now, unless this is like a rectangle or a circle or something, we don't just have a formula for that, right? We don't have pi r squared for some random shape that I just drew on my whiteboard. But certainly, that is an actual physical area. And it is certainly something that you can imagine having a formula like pi r squared for, but how would you find that formula? What piece of geometry is going to give it to you? The fact is, the piece of geometry that gives you the formula for something like this is calculus. That is the part of geometry that allows you to find the area of almost any shape. The area, the shaded region, is called the definite integral. And by integral right now, we're going to take this to mean area. It's a little more, actually, no, we're going to leave this. The integral refers to the notation. But a definite integral, notice this word is not the same as interval, is the shaded region under the curve. On the interval, in this case, oh my gosh, I ran out of room. I'll just put y equals f of x. On the interval a to b, right? From a to b, we want the area under the curve. The name of that is an integral, a definite integral. Why is it definite? I'll just tell you, it's definite because you're telling me what the endpoints are. You don't tell me the endpoints, I can't give you a definite integral. At that point, it's indefinite what it is. The definite integral is the name. It's the technical term for the area I've drawn there. All right, that is a definite integral. Integrals have to do with areas. What's amazing isn't just that I'm defining this. What's amazing is how the integrals have to do with the functions. Because the area is like a new function of the function f of x. It's a new function, that area, just the same way that the derivative is a function. And if you make a definite integral, just like when you take the derivative at the tangent line at a certain point, that's like a definite derivative, it's at a point. You've defined the point you're taking it at. If you take the integral on a definite interval of the x-axis, calculus works in a really beautiful way that is just as nice as what we've been seeing with derivatives. Areas, it turns out, work just as nicely as derivatives. But we need a new notation for that. The notation for that area for the definite integral is this. We write a long S symbol. That's the integral symbol. The integral symbol is a big S because it stands for sum. Taking a sum, adding things together is like doing integration. Integration means combining, bringing together disparate elements. And it's an integral, and it's from A to B. We're putting in endpoints here. I'm gonna make A, so just, there we go. From A to B, the left-hand side goes on the bottom. the right-hand endpoint of the interval goes on the top. So A goes on the bottom. That's this point. And it goes to B. So this is saying from A up to B, what's the area under the curve? Well, now you have to put the curve in. But before we put the curve in, I have to say that this notation isn't done yet, because this notation also needs to tell you which axis A and B are on. I'm just saying, right? How do you know you're not finding the area going from here to there? So we're going to put the function in here, but we need to leave a little space. We put dx at the end. So this is like bookends. There's a left-hand symbol and a right-hand symbol, and these always go together when you do integrals. You never write that symbol down without having another symbol on the right-hand side to bookend it, okay? What goes in the middle is your function. This is the integral. It's the definite integral of the function f of x on the interval a to b. That's how you write the area. You write it in these symbols. And so just the same way that the derivative represents the slope of the tangent line in geometry, and it represents the rate of change of the function in sort of the algebraic sense. In the geometric sense, an integral, this symbol, let me take away all these extra lines. It looks very messy. The integral symbol, when you see endpoints, it represents an area. Just like when you plug in x equals a, the derivative represents a slope. But more generally, the derivative doesn't represent a slope, it represents all possible slopes, right? Just if you write f prime of x, not f prime of a. That's like all possible slopes. You give me an x value and I'll tell you the slope. That's what this is like. If you took away the endpoints, so it's not a definite integral, well then it's like it's a function. And you have to give me the endpoints to get the actual number that is the area. Areas are numbers, it's a measurement. See, like you can see on my whiteboard here, it's like a number of squares inside that area. In any event, areas are definite integrals. On the other hand, you might be like, okay, teach, you're telling me that functions as formulas have derivatives that are formulas, and functions as graphs have derivatives that represent slopes and rate of change. And functions as graphs have integrals that represent the areas if they're definite integrals. So what is the equivalent thing for functions with graphs? Or rather for functions with formulas, sorry. What's the equivalent thing with functions formulas to the derivative of a function being another new function? What's the equivalent for the area? Because what if you don't specify the endpoints? You end up having an indefinite integral. An indefinite integral, no endpoints specified, right? You're not giving me the numbers to plug in. This is kind of like a derivative before you plug in x equals a. The indefinite integral is a function, just like the derivative is a function. If you take it as f prime of x, it's a function. And so it's not a number like an area. It's not like something square meters or something, the indefinite integral. And in fact, what kind of function is it? You would write this. Notice I put an integral symbol and a dx over here, and then I put the function in between. You have to have both. If that's not x, then that's not x either. Cool? An indefinite integral looks like this. This is an antiderivative. Definite integrals are antiderivatives. This is the function version of what an integral means. antiderivatives are kind of like the opposites of derivatives. And in a similar way, integrals are kind of like the areas, rather, are kind of like the opposites of slope. We'll talk more about that in the next mini lecture. Now, what if your function looks like this? Notice it's above the x-axis here, but it's dipped down here below. Now, I said before that I wanted to find, let's say that that's the point B. Let's say that this is the point A. If I want to find the area under the curve, that would be given by this notation. The integral from A to B of the function f of x with respect to the variable x, this represents this area under the curve. But there's a caveat here, and I just need to point this out. In the physical world, as well as in geometry, areas are always physical quantities, right? Like there's no -3 square feet. That's not a thing in our world that we live in or that we can create on paper in geometry. Negative areas aren't real quantities. They don't exist in the real world. However, neither do negative curves in a sense. What I mean is that in the real world, all lengths and distances are positive. You can't measure negative distances with your ruler unless you just mean backwards by that. Negative in the physical world usually means it has an interpretation. It doesn't mean literally negative. Like there is no -1 inches. There's 1 inch backwards. There's not -$1 in my pocket. There's $1 deficit in my account. There's not like, you don't like fall down to the ground 3 feet. I mean, you don't fall -3 feet to the ground. You fall down 3 feet instead of up, or maybe it's the other direction, whichever one's negative in physics. In any event, the point is that negative has a meaning in the physical world. Negative doesn't mean the same thing in math. In math, negative numbers are totally legit numbers. They don't need interpretation. They're just points on the number line. And on the number line, these y values are positive, and these y values are negative. And in the area, the difference between a definite integral and an area in geometry is that the area under the curve is positive because all of these values of the curve are positive. But if the curve is below the line, below the x-axis, then we're really looking at the area above the curve, not the area under the curve. And the area above the curve actually gets a negative sign. Like if this is 10 and this is 5, then the total area is going to be 10 minus 5. I'm just saying areas underneath the x-axis get a minus sign. That was my caveat. Because these aren't your old school physical areas anymore. These are new function math areas, and negative numbers are just as good as positive numbers in the universe of mathematics. We're just limited by living in a physical universe to having to always consider only positive quantities.